have to go over. That doesn't quite get in the top. Yeah, it gets it in enough. Okay. I wonder if I can. No. Okay. Oh, well, people will hear me read it. Okay. So I think so. Last year I did this thing, and I did the video, and I had the blackboard and everything. And I seem to remember it was much fuller. So maybe I covered more stuff last year, but I don't think so. I mean, okay, at the end when we were doing graph algorithms, I got really bored with graph algorithms. So I stuck in things like group testing and pattern matching and fun stuff for me that I didn't do this year. But I didn't think it was, maybe I just wrote more details last year. But anyway, those videos, I think you can find the videos from last year, right? Is this recording? Yeah, this is recording. Ah, I have to start this thing. Okay, hello, anybody there? Can anybody, has anybody seen the videos from last year? They're also on the YouTube channel. Oh, okay. So they should be. So I'll post somewhere, I'll post the link to the YouTube channel that has all the videos from last year. If you go to the end, I mean, if you look at stuff and you're like, I have no idea what this is, I've never heard of this, it's probably because it's something I threw in last year that we didn't do this. I think almost everything we did this year, we did. I'm not sure if everything we did this year we did last. Anyway, okay, so let's just zip over what you should know. Okay, so remember there was this clink versus boom thing where I said there are easy problems and hard problems, and you can't say I'm not interested in hard problems because I don't want to waste my time trying to do something that nobody can do. Like people for 50 years have been trying to do this stuff. Nobody's got anywhere. I just don't want to know about it. And remember I said you don't have that option because there are hard problems all around us. And if you take an easy problem and you just tweak, you change one number from a 2 to a 3, and it becomes hard. So there are things, and is this going to show up on the final exam? Yes, probably. Where, like you change something very slightly, it goes from being easy to hard. And so you can't, so the two things you have to remember is hard problems are everywhere. You can't avoid hard problems. You have to learn how to recognize them, how to deal with them. Although mostly dealing with hard problems is going to be algorithm Norbert's. The other thing is it's fun. Like you go over and you can have fun with hard problems, and you can also you have cryptographic applications. So the lessons are, first, hardness is unavoidable, and you don't want to avoid it anyway. And the other thing is you can't just pattern match. You can't just think, oh, this looks like a problem I've seen before. Yeah, well, okay, it's an exam, but I can try to make it some fun for me. Not sure. Okay, so I think they're cute questions. I've come up with the questions and I think they're kind of fun. I mean, to the extent that an exam question can be. Okay, so the two things are, don't just pattern match. Don't just think, oh, this looks like a such and such question, I'm going to do it with that. oh, I've seen a problem like this and it was solved with greedy algorithms. Blah, we do it. Like, no, because remember I had that thing where you said, okay, partition it into increasing subsequence, greedy algorithms. Find the longest increasing subsequence, dynamic programming. Okay, you can't just think, oh, this looks like a problem I've seen before. I remember the solution. I'll just write down the solution for the version I've seen before and hope that I will get most of the marks because, if the problem hasn't changed much, maybe the solution doesn't change much. That strategy doesn't work. What else was there in Clink versus Bloom? So that was the first time we saw Hampa. We saw like, you have Eulerian cycles and Hamiltonian cycles, and one is easy and was done like they asked Euler and he just did it. And then Hamiltonian cycles is like hundreds of years later, we still don't know how to do it. And we think there is no holy. Okay, so then we started with divide and conquer. And the first thing we did, because I didn't want you to get the impression that divide and conquer, we're going to start with the easy stuff. We're going to start with, weak techniques, because all you do with divide and conquer is sorting. No, so I didn't want you to think that. So we started with graph coloring, which is hard. So we did this coloring planar graphs, where you have separators and you can split it in, and I'm sure everyone remembers that because I wanted to sort of shock you right at the beginning of the course. And because that was still, when I did that assignment, it's still in the time frame, in the window when you can quit the course and get your money back. So anybody who was, I'm not sure I want to take this course, be like, okay, well, this is sort of what it's going to be like, and then they had a chance to escape. So the people who didn't escape, it's like, well, you were warned there. So coloring graphs. So you probably remember how that was. Then we did Euclid's algorithm, which is in a divide and conquer algorithm, but it was sort of, nice. What is an algorithm? Sort of the oldest algorithm. And it got us into talking about models of computation, because you think, okay, well, how hard is it to do an arithmetic operation? We're talking about complexity of adding, complexity of multiplying, because you have the number of steps. When you have Euclid's algorithm, you're saying, does this divide that? And take modulus, take something A modulo B, and say, okay, how is this? So you count the number of steps, but that's assuming that this is constant time. And it's like, okay, if it's human being, it's not actually constant time. So you're talking about the models computation. This got us into talking about Karatsuba's algorithm and how hard is multiplication. Remember, so down we finished talking about Kolmogorov complexity, and I mentioned that Kolmogorov was the person who made that conjecture that multiplication takes quadratic time, and Karatsuba in one of his seminars, and Karatsuba went away and proved it, and then Kolmogorov sent the proof in with Karatsuba's name on it. And then we did Strassen's matrix multiplication, where you cut it and you sort of do this sneaky thing where you, remember Karatsuba, you have the two numbers, you cut them each in two, and then instead of doing 4 multiplications, you do 3. And then with Strassen's, you take the matrices and you cut them in 4, and then instead of doing 8 multiplications, you do 7. Now, with Karatsuba, it's fair for me to ask you to memorize the formulas for Z0, Z1, and Z2, because they're easy. I mean, you can sort of recreate them. I am definitely not going to ask you to memorize the formulas for the M intermediate, the computations to compute the intermediate matrices, the MIs for Strassen's, because that would be sick. I don't think I know anybody. Maybe Strassen has them memorized, but I don't know Strassen. So it's probably fair for me to say I don't think I know anybody who's actually memorized. Then there was the fast Fourier transform. If anybody has questions while we're going along, please post them in the chat, and I'll try to actually, if I close the chat, then I see, then a little flag will pop up, and I will see that there's a question. Otherwise, yeah, maybe it pops up anyway, or like click the raise hand or something. We did fast Fourier transforms, so yes, you can use the lecture notes. I was thinking about it. Yeah, that's fair. So in fact, I guess even if I'm trying to talk to somebody to get this respond this walk down browser, blah blah blah. I don't know if I'm actually doing that. But if you've downloaded and you have it in a PDF, then I guess you can actually just have the lecture notes, and you can also do a search, because I never got around to adding an index, which LaTeX does a nice index, but I haven't got one for the lecture notes yet. So you can just search and click and jump and things like that. So you don't have to print it, because I would feel bad for the environment if I made 99 people print nearly 200 pages of lecture notes each. So please don't print it. Okay, fast Fourier transform. So yeah, you can have the lecture notes. Fast Fourier transform, you do not have to know. I think I promised when Max taught it in the lecture. I actually did the lecture notes for it, partly because I never saw it when I was an undergrad, and I have sort of a very shaky relationship with it. So I thought it's actually time, if I'm making you see it, it's time I finally learn it. I'm not sure I did learn it. I knew it, I understood it when I finished writing that chapter in the lecture. So I definitely know it better than I did at the beginning of the course, but I'm still not going to touch it. Asymptotic bounds. So this is all about best case, worst case, average case, blah. But key thing to remember is worst case is not big O. It doesn't mean the best case, worst case, average case, and big O, theta, big omega, little o. These are orthogonal things, right? Big O is at most about, little o is less than, about. Theta is like more or less about. Big omega is at least about. Little o is bigger than, and stuff like that. But you can say, like, in the best case, we use at most about, or at least about, right? These are so big, like big O is an upper bound, big omega or O or low, or big omega or little omega is a lower bound. It's just saying, and then theta is saying, okay, within a constant factor, we have a tight bound. So asymptotic bounds, know that stuff. Sorting, and also the master theorem, or what I call it. I don't know if that was in sorting or if that was in asymptotic bounds. And my marker is dying right at the end of the course. The black. Everything else is good. Maybe the blue is maybe. Well, even the blue is fine. Sorting. So analysis. So we didn't just do merge sort and quick sort. Remember, we said things like, okay, best case analysis, for example, insertion sort. What's the best case for insertion sort is actually linear. Remember, because it's if the things are sorted in, or if you're given the list sorted in reverse order, then it's actually just linear because you always insert things at the front. And then we were saying, okay, so we did merge sort, and then we did quick sort, we did quick select. And so this is how we did the average case, and we got a bit of randomization in there and stuff like that, which is one of the learning objectives for the course. Okay. Questions? No, I think we're still. No, yeah, okay, we're still good. Okay. Greedy algorithms. So the thing is, like, I don't want the final to be a surprise. Can you more or less figure out what's going to be on the final? Will there be a question about greedy algorithms? Yes. Is it likely you're going to have to write something that goes like, before we take any steps, our empty sub-solution can be extended to an optimal solution. Assume that after I steps, blah, blah, blah. I mean, yes, it's quite likely that you're going to have to write that, or at least know that, or because we've done it ad nauseum. There was a reason for that. I want you to know that. And it's not just because so how to say it? If you're designing algorithms, greedy algorithms are really useful. That's quite likely. I wouldn't be surprised if something like that showed up on the final. I'm not making any promises one way or the other, but will there be a question about greedy algorithms? Yes. Will there be a question about divide and conquer? Yes. Will there be a question about dynamic programming? Yes. Will there be a question about empty completeness? Yes. Will there be a question about graph algorithms? Yes. Will there be a question about diagonalizations? No. Okay, I'm letting you off the diagonalization. But is it, am I going to hit these? Yeah. And the thing about I figure like the course is 3 months, so you have like 1 hour for each month. But look, it's not that. It's like 1, 2, 3, 4, 5. 5 topics. I mean, that's not. You could get like half an hour for each topic. You haven't seen the questions yet. You're just making that assumption on the basis that they're my questions. I don't ask easy questions, but maybe I do on finals. Okay. I didn't in the past 2 years, but I think the questions this year are easier than the past 2 years. So I'm also thinking, I think they're easy. I haven't, like, I have a selection of questions, and maybe I'm going to throw some away, or maybe I'm going to give like 1 or 2 of them might be bullet or something like that. But I think the course has been like a reasonable algorithms, 3rd-year algorithms course for pretty much any university. Reasonably hard, but not to the extent that if you showed somebody this list of things we've covered, almost anywhere in the world, they say, yeah, that's a solid, good 3rd-year algorithms course. I want to be able to, if I show somebody my final exam, and they'll say, yep, you can pass that final exam. You have a good working knowledge of 3rd-year algorithms. No. So the thing is, I mean, no, you won't have to. Would we have an extra 5 minutes? Yay, I'm still thinking about like, I'm still thinking about the details. Like, I'm not sure, maybe it'll be 9 to 12. Maybe I'll give you a little bit extra time because like there doesn't seem to be an exam that afternoon. Does anybody have an exam that afternoon? I mean, I know there are only, how many of you are there here? In 10. So 10% of my class. Does any of this 10% have an exam that afternoon? Anyway, if somebody's watching this recording, email me and say, okay, you have an exam that afternoon. Otherwise, I might give you a bit more time. If it turns out, I have to admit that the exam is kind of fun. I usually send my exams to Alex and Norbert And then sometimes if they come back and say, no, no, this question is ridiculously difficult, or if they actually say they can't do it or something, and I tone it down. I can't really do that. I mean, last year, yes, I gave people between 7 in the morning and 8 or 9 evening or something like that. But this year, we're supposed to be back to you write a synchronous final, and so things are supposed to be getting back to normal. And I have an exam. I was given the morning slot on August 5th. So that's rough. If you're on like the other side of the Pacific. It's also rough if you're on this side of the Pacific, but on the West Coast. Then it's kind of annoying because that could be like, I guess it's actually really, really bad if you're in Hawaii or something. Because then it's not in the evening, it's like it's like 1 in the morning or something crazy like that. I don't know. I mean, does anybody know what the other professors are doing? Like there's a 31, 36. I know last year, Alex also gave people 24 hours. Or he gave people like from the start, yeah, I think he gave them 24 hours. And I just gave them from the 7 in the morning to 9 at night or something like that. But anyway, okay. I'm curious. I think the Dow's policy of inclusivity precludes me calling a time zone weird. I am not so okay. If you are in a weird time zone, to email him. I don't think I'm allowed to say this whole strip of the Earth is a weird time zone. So to try to not be very centered on Halifax, I'm not going to say that. Okay, what? So, I'll think about it. Like I might do what I did last year and say, look, okay, people can have. It might. I mean, in that case, I'll add a bit more to the exam to make it reasonable for a longer time frame. I'm trying to get back to normal. I don't want it to be, but maybe something like that. I'll write the exam and then look at it and think, I'll write the exam, I'll send it to the TAs and ask them how long it takes for them to do it. If they come back and say, because usually the factor is something like, if we're supposed to multiply by like times 10, whatever it takes us to write the answers, and times 4, whatever it takes our TAs to write the answers. So it's a 3-hour Brightspace exam that we can take anytime during exam week. But in that case, I mean, are they doing this weird thing where you have a bank of questions and will select their questions randomly and blah, blah, blah? I don't really like that. It's not, Okay, so for example, it's absolutely, I do not do multiple choice. I mean, okay, the multiple choice is like that easy, like you apply the master theorem thing, like, is this big O, this, is this big O? Like I do multiple choice for that kind of stuff. But for algorithm design, it's too painful to design the questions. One last test scheduled for during exam week, where it's the scheduled breakaways. Yeah. So I mean, the nice thing about having final, I mean, it's bad having an online. The nice thing about it, actually, okay, we should get it. The nice thing about having a final is I haven't really been trying to, I mean, I can't catch people cheating this year. I mean, you can go through, you could have somebody else do the whole course for you and get credit for me. It's like, oh, okay, here in the pandemic, that's not I can't do anything about that. In a normal year, it's like that you're writing the final and you have your student card with your photo, and so people like, yeah, okay, fine, you could get like a doppelganger to write the final for you. But you know, there are checks in place, and that's why we have this policy usually that you have to pass the final to pass the course. So that even if like people see, then there is this final check that you actually did learn it. So my priority this year has not been to make sure people are not submitting, people are not copying and stuff like that, which normally I would. It's not the fun part of my job, but normally it's like part of my job. This year I'm like, yeah, okay, now is not making me do that so much, so I'm just not going to try, because really there's no way I can catch it. But the final is still some sort of attempt at that. You know, the final checks to say, like, did you actually learn this stuff? At some point in the course, you have to have all the material in your head at once. So speaking of which, let's keep going. So greedy algorithms. I have to restart the timer. Greedy algorithms. So Huffman coding. Remember, I did this sneaky thing where I made you sort of rederive the correctness of Huffman's algorithm by pretending that we were sorting, figuring out how to merge lists. Minimum spanning trees, and then so this was nice because we saw Kruskal's, Prims, Barocas, and then we talked about like, okay, with Kruskal, why do you need all of these? So Barocas, for example, you can do it in parallel. Kruskal's, it sounds super easy until you find out that you need a union find data structure, which we hadn't learned until that point. So Prims, you need the priority queue. So it's actually, once you know how to do a super fast union find data structure, it's slower. But you have things like, okay, Prims, you always have a tree. Krustals, you don't always have a tree. So Prims, you're just adding things onto the tree. So like if you had road building material, road building equipment that can't go over a dirt road unless it's paving it, then you want to run Prims instead of Krustals. Okay, so this was this the first time that we saw Van Leuven's algorithm for building a Huffman code that used priority that used two queues. But this was sort of the first time we saw a data structure where we really needed a sneaky, cool data structure to make our algorithms run fast. Then we did more greedy algorithms. We did activity selection, Superweight's algorithm for partitioning a sequence into the minimum number of increasing subsequences. There should be an R in there. It should be two approx. For vertex cover, that was where you find a maximal matching and then take both ends of each edge in the matching. And that gave you because each edge has to be covered, at least one of the endpoints has to be in a minimum vertex cover, I mean any vertex cover. And then you say, okay, and you can't get two of the edges in the matching with one vertex because you never share an endpoint, because that's the definition of a matching. So you know that the minimum vertex cover is at least half as big as the vertex you get, so you get a 2 approximation. So this was the first approximation. Maybe it was anyway. It was an approximation algorithm. Then we saw vertex cover on trees, and we saw fractional knapsack. So fractional knapsack is when you can cut the stuff. And this was the chapter where it was like, where we did ad nauseum. Before we take any steps, our empty subsolution can be extended to modules and blah, 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 blah. This came up over and over again in that chapter. Okay, so that was greedy algorithms. Then, sun is starting to shine. Then we started on dynamic programming. We didn't have a lot of chapters here, but it's an important section. And some of the chapters here were quite dense and long. So there was edit distance and also longest common subsequence. So this was where you have those, remember the black and red arrows that you can go across. If for edit distance, you can go across the red arrows for free, and for longest increasing subsequent, and the black arrows cost you money, and then for longest increasing subsequence, the black arrows are, you don't get anything, and the red arrows you get paid for going across. And so we did alignment, which I'm sure everybody loves, because that showed up on at least on an assignment, and I think also on a midterm. Yeah, so everyone should remember alignment. Then we also did local alignment, which I put on the exam I put on the exam 2 years ago. So edit distance, lots of stuff there. Subset sum and knapsack. So now we're talking about binary knapsack. So you can do these with dynamic programming. We got into this idea of, how do you measure the complexity of the algorithm? You measure it in terms of the size of the input, that is sort of the size of the piece of paper I need to write the instance. And so if I'm writing a number, the size of the piece of paper I need to write the number is going to be logarithmic in the magnitude of the number, unless I'm writing in unary, in which case it's going to be linear. The base of the logarithm, of course, the base of the number system I'm using. So, but that doesn't matter. That doesn't change things by more than a constant factor, unless the base is 1, in which case it's unary, in which case things are linear. So, and remember, we illustrated this by saying factoring. I encourage everyone to watch the movie Sneakers, about what happens if we figure out how to factor quickly. It's traditional for people to mess up and say factor prime numbers, which is pointless, but you actually want to say factor large numbers. But it's easy to make that. I have definitely done that sometimes. I'm not sure if I did that in this case. Okay. So the illustration is like, can you write a program that takes times linear O of n steps to factor a number n? So yes, that's really easy. You write a for loop for I equals 1 to n. 2 to n minus 1. 1 to n, because if you include 1 and n. So you get a list of all the factors. 2 to n minus 1 if you're checking if n is. Forget the details there. So then we did optimal binary search trees. So this was, remember you say, okay, suppose we have a subtree, and we have the optimal binary search tree on keys I to j, and now we have that for all of the subtrees of size up to like s minus 1, and now we're going to try to do it for size s. So thus we like filled in the diagonals. Okay, and then we did Camus speed up where we said, okay, that was on an assignment, I think, where we did this thing like if you add stuff to the right. Okay, you don't like. I'm not going to ask you about Camus speed up. But so remember how to build optimal binary search trees, longest increasing subsequences. That was another one where we needed the data structures because you need range max, dynamic range max data structures. So and why? Because so you do this thing where you have. Do people remember how to do the longest increasing? So if you do it naively, you have to scan for every time you look at SI, you have to scan through S1 to SI minus 1 to find you have this array that says for each of these numbers, how long is the longest increasing subsequence that enter that number. So you scan this. And for everything that is smaller than SI, you check and you choose the maximum, blah, blah. But if you have this data structure, then it becomes analog N. So, yay, data structures. So even though there were only 3 chapters, it was quite a lot of material. And then you also had the assignments with other dynamic programming problems on them, which I didn't write on the board. Maybe that's why it's not as crowded this year as it was last year. We did NP completeness, and so I should have underlined this, because even though it was only 1 chapter, it was a biggie. So there's reductions, the idea that I want to be able to A reduces to B, so reducing turns into, somebody pointed out that reduces sounds like it gets smaller. But we're usually, a reduction means that the thing that you reduce to is at least as hard. So somebody was complaining that it's counterintuitive. Just think of reduces as turns. So if A reduces to B, and we have a polytime in polytime, and we have a polytime algorithm for B, then we have a polytime algorithm for A. And this means that we have an instance for A, we can turn it into an instance of B, such that the instance of A is a yes instance if and only if the instance of B is a yes instance. Okay. So we did lots of reductions, ranging from the very simple, so reducing independent set to clique and vice versa, and vertex cover to independent set. And then we did all our, so we had independent set and clique and vertex cover. Actually, so these 2 are easy and these 2 are easy. So that means these 2 are, and then we did the reduction from 3 sets to clique. Actually, we did the reduction from 3 set to independent set because it involved me drawing fewer lines. Usually it's I think in the textbook it's 3 set to clique. And we did clique to set. And then obviously, if you can do set, you can do 3 set, special case. And then you had this wonderful Satan transform for turning blah blah, and then we had coloring, and we had hand path, and we had all this kind of stuff. So that was all in reductions. So we should be pretty good at reductions by now. Although, to be fair, I'm not going to ask you for a hard reduction on the exam because everyone would fail. Almost everyone would fail. Possibly everyone. Possibly almost everyone. If I'd had to write hard reductions on my finals, I would have failed. So I mean, I could put it on as a bonus question because it's always fun to identify, like if somebody gets it. So I'm not going to do this year because Val would probably not approve. But when I was teaching in Finland, and in Finland you're allowed to do really hard things because I don't know. So at one point, I working with my former PhD supervisor, we solved a problem. We'd come up with some really cool trick, and we wrote the paper at the same time I was preparing the final. So I put the open problem, I put the problem that we solved in the paper onto the final, I think as a bonus question, but with a big hint. And so 3 people actually got it. And then, yeah, and I think the paper got accepted. Maybe it was the final. I think, or maybe when I was preparing the final. Anyway, I actually had the chance to tell everyone when I was announcing the marks, the paper had been accepted, and also to congratulate the people who figured it out. It wasn't like it was a big hint, but I was still super impressed because now, admittedly, it was a class of 30. So 3 people was actually a lot. It was also only like a 3-hour exam. But I'm not going to do that this year. See, that's what I said. Like, you can have fun with finals. That was like lots of fun. Okay. Cook's theorem. So, sort of know Cook's theorem. I mean, you should know Cook's theorem just in general. By the time you get out of this course, you should know Cook's theorem. You should sort of know why it's true. I'm going to promise that you don't have to know. You don't. You should know something about Turing. I mean, remember something about Turing machines, just because otherwise, if you go out, you meet somebody who's done complexity theory and stuff like that. You don't know what a Turing machine is. So the reason I know this is because if you don't know, people will laugh at you. Maybe not openly, but for example, I remember when there's a language called Turing, which I had to learn at Queen's because it was like a collaboration between like some prof at Queen's and some prof at U of T, I think. So it was only ever used in like some high schools in Ontario and like 2 universities. I don't think it's used because, but it was sort of like a C clone language. Yeah, it has some nice stuff. I don't remember anything about it, but yeah, it was Queens's little personal, like private language, so we had to learn it. But the key thing, it was taught at some Ontario high schools. So when I was in grad school, I was in the scuba club, and one time for reading week, we went scuba diving. We went to an island and we scuba dived for a week, scuba dove, whatever it is. And there was this one super annoying guy on the trip who, unfortunately, so we got paired up, and we had this. So I was in the same room with him, so I was totally sick of this guy. And So one time, so somebody was asking me what I study, and I said, oh, so like computer stuff. And they asked me like this. I said, no, like theoretical computer stuff. So I, Turing machines and stuff like that. And this guy said, oh, Turing, we learned Turing in high school. So I didn't say anything because I just didn't want to have another conversation with him. But I thought, okay, before he said that, I thought he was probably a moron. But when he said that, I was sure he was a moron. So it's important to at least sort of know what the Turing machine is, to know that a Turing machine is not something that passes the Turing test or something like that. It's so to avoid saying things like that and have your scuba diving partner think you're an idiot. It's important to know what a Turing machine is. So Cook's theorem, you should know what it is, and you should have some idea how it's proved. Okay. More graph algorithms. Did I restart the timer? Yes, I did. Okay, more graph algorithms. You should know depth first search. No kidding. You're in third year computer science. You should definitely know depth first search. In particular, you should know topological sort and strongly connected components. And I will forgive you if you aren't sure whether or not to put a hyphen there, because neither am I. I have a feeling there should be, but I don't think anybody puts it. And breadth first search, you should know breadth first search. So I was trying to show you this thing about in one of the years. Oh, so I was talking to some people yesterday, and they are still traumatized by I put the cabbage, the goat, and the wolf question. People usually do this in AI. They used to do this in AI classes before AI became just machine learning stuff. But you have this thing of okay, figure out how to you're on the side of the river and you have a cabbage, a goat, and a wolf, and blah, get the three of them across the river, but you have a boat that only carries one of the cabbage, and it's just a safe space. So you're doing this kind of stuff now with water jugs. So that's a BFS, and then there's Dijkstra's, and Dijkstra's is sort of a BFS, but with a priority queue instead of a queue. So you should know Dijkstra's. Oh, actually, that note to self: don't waste time on the bonus question. So when my first year in grad school, so yeah, don't usually. This is terrible exam taking strategy. But I would always go for the bonus question first. It was usually the most interesting. And I was in Cook's logic class, and I spent the whole exam trying to figure out the bonus question. And in fact, I think I got the bonus question. I got it at the end, got it. And I think I got one other question out of 10. But I was the only one who did the bonus question. So somehow I passed. I'm not sure how that happened. Okay, but yes, in general, don't do that, because then I would have to fight down to be able to pass you or something like that. Now there are all these rules and regulations, so I can't just randomly assign marks. Bellman-Ford. Okay, so this is if you have negative weight edges, but you don't have negative weight cycles. Matrix. What we're calling matrix multiplication, which is actually like min plus, right? Where normally matrix multiplication, you do a sum of products. Here you're doing a min of sums. Okay. And Floyd-Warshall, where this is sort of like the matrix multiplication, except instead of multiplying it, you're saying, okay, what's the shortest you can do from here to here using only intermediate vertices up to vertex K. Okay, so this gets rid of a logarithmic. So here you use repeated squaring, so you get n cubed log n, and here you get n cubed. Network flows, these should be still familiar, still fresh in your mind because we saw them just last week. Remember, you write the capacities, and then sort of choose a flow, and then you write the flow over the capacity, and then you build this residual, which is the tricky thing is you have so the edge, the amount in either direction is you have to if you have a flow going this way, then you can reduce it by that much. So you put sort of an edge with that much going the other way. You can change it. So reducing a flow from A to B is like adding a flow from B to A, blah. It's in the book. Oh yeah. So you can use the lecture notes, and remember I posted sections of the CLRS because I didn't get around to writing lecture notes for this stuff. Actually, I skipped over this. You do not have to know zero knowledge proofs, and you do not have to know fine-grained complexity. So, also because I didn't write the lecture notes for those, and I didn't write the lecture notes for this stuff, but I posted sections of it. And network flows, and you do not have to know diagonalization. So the halting price, so the countable and uncountable infinities, the halting problem, Kolmogorov complexity, fun stuff like that, except it's on assignment 8. Somebody's whistling outside my apartment. Oh, look, so so we only used 2/3 of the lecture time. I must have gone much easier because last year the board was full and I used the full 90 minutes going over what everyone had to know. This is weird. It felt like a full course this year. Okay, I'm going to reset this and then I don't know, answer questions. Actually, I think while we're recording, I am going to take the camera off and record my whole setup here because it's so awful that I'm proud of even having tried to do a course with this arrangement. I should probably have tried to build something, but I'm better at sort of algorithm design than my father was a civil engineer. But this is my drying rack. This is my chair, other chair. This is the little camera. The laptop is sitting on top of what used to be a Mandarin box. And you have the phone keeping, oh, right, we keep track of the phone timer again. And my den, which has been converted into a lecture hall, very small lecture hall. I am so looking forward to having real classes again, where you have a blackboard, you have space, you can push the blackboard up, and you have another blackboard that's as big as this whole thing. That was algorithms. I can try. What do we not need here? Don't need this. Okay. Oh. what I should do is take a picture of this. Before I start erasing things. No, that's not great, but it'll do. Okay. Actually, I mean, I don't need to worry about taking a picture like this because these are just the chapter cuttings. So, okay. How does caret pseudos work? Okay. So suppose you have some number, you have these two numbers, x and y, right? And you want to multiply x and y. And suppose that these are n-digit numbers. So n-digit numbers. So what we're going to say is this is x1 times e to the n over 2. Actually, I think this was an m at some point. Right. So if this is, if x equals 5, 1, 7, 4, 9, 6, 7, 2, and y equals 2, 3, 8, 5, 4, 4, 8, 1, 4. Okay. The base, okay, if the base is 10, what would come next? Honestly, for me, after this course, I would take a short holiday. Maybe like relax for a few weeks from other complexity classes. Okay, so first of all, we haven't seen everything. In divide and conquer, there's a classic algorithm called convex halls, right, where there are other algorithms, but it's classic. The domain, if you follow the link to the FFT lecture and you click, then you have domain's other lectures. And he does the convex hall. So basically, a convex hall, you have a bunch of points. And a convex hall is a shape, the minimum shape. So you have to, sorry, it's convex, so let's put one. So it has to be, so it's the smallest convex shape that contains all of the points. Okay, so this comes up in lots of stuff. How do you find a convex hall? So the divide and conquer, I forget, this actually, the algorithm has a name, I forget the name. But one of the things you can do is you have the points. Okay, well, you sort them by x coordinate and you split them, right? And if you have the, well, okay, let's say that we split them here. This is one, let's do that one. I'm doing this because I actually really wanted to show this in this course. I just didn't really have time because we were getting close. we're in divide and conquer, and I realized we spent a lot of time on divide and conquer. But that was because we had to do asymptotic notation as well, and we were sort of covering some of the basics are packed into divide and conquer, but it meant I didn't do this algorithm. So if you find the convex hull of this side and of this side, and then you say, okay, now how do you put those two together? Well, you can find here, you consider the lines and you walk around until, if you go any further over here, the line between this and this point intersects this shape. And then from here, you walk around. So you start at the closest, and then you start walking around until if you walk any further on either side. So you're here. If you walk here, the line is going to intersect this shape. If you're here and you walk here, the line is going to intersect this shape. So you say, okay, I add those lines, and then this is the convex hull of the whole thing. So there's a nice divide and conquer that does convex hulls. We didn't do any computational geometry, I think. Did we? We maybe didn't. No, I don't think we did. So there are a whole, Domain is famous for this computational origami. It's fantastic. I can send you. Oh, I'm not wearing my. Oh, actually. I was wearing this when I went out this morning. So the conference is WADS 2009. So WADS has a terrible name, but it's workshop. It was originally workshop on algorithms and data structures. Now it's symposium with algorithms and data structures, and W doesn't stand for anything anymore. So WADS 2009. So Domain is from Halifax. I think I said that before. He was a guest speaker at WADS 2009. So Meng, or Mung, if you can actually, if apparently that's how his name is supposed to be pronounced, he's actually running WADS here, WADS 2021 in a week or two, I think, at Dow. So anyway, at WADS 2009, Domain was an invited speaker. He did this cool thing. He has a theorem that says, if you take a piece of paper, the plane, and you draw a collection of dots, lines, and polygons, he has an algorithm that will fold the paper, and such that if you make a single cut, and then when you unfold it again, you've cut out exactly those dots, lines, and polygons. So and also he's got other variants, like you can draw a bunch of blue dots, lines, and polygons and green dots, lines, and polygons. He can find a way to fold it such that there's a blue line and a green line. If you cut the blue line and unfold it, the blue dots, lines, and polygons have been cut out. If you cut the green line and unfold it, the green dots, lines, and polygons have been cut out. So anyway, at the conference, he did this with a maple leaf. Like if anybody has ever tried to cut out a maple leaf, it is not that easy. So he had a piece of paper with a drawing of a maple leaf with a bunch of lines on it, and with instructions of how to fold these lines, which became valleys and which became mountains. The valleys is when it's like this, and mountains is when it's like this. So how to fold it, and then there was one line, you cut that line, unfold it, and you have a perfect maple leaf and a perfect silhouette of a maple leaf. And I can't usually get that kind of stuff to work at all, but even I can do this. So I still have the PDF lying around. I can post it on Brightspace. So computational geometry is tons of fun. We didn't do any of that. We didn't do, like the 2019, I did a streaming algorithm for something called iceberg queries, and which it's got constant space complexity. Like, we didn't do anything like that. I mean, no, the CLRS is huge, and there are all these other topics, so it has some computational geometry in there. We didn't do most of those. I don't think we did. Did we do any of them? We didn't do, apart from Huffman's algorithm, we didn't do data compression. without getting, algorithms is a big field, and it comes up everywhere. I mean, nowadays everyone's like the algorithm. They're making movies about this. Most people make the movies about it. Although actually, yeah, okay. So this movie wasn't. I was going to say just today I was reading something by Chazelle, who is a CS professor at Princeton. And if anybody's seen La La Land, it's directed by his son. Damien Chazelle is Bernard Chazelle's son. So actually, there are people in Hollywood, and also a bunch of like this guy who was a professor at Princeton, where Jeffrey Westbrook. So he wrote a really nice PhD thesis, graduated from a top school, became a professor at the top school, and then packed it in and went away and to become a writer for The Simpsons. So actually, there are people who are writing accurate. And I think I mentioned in one of the lectures that Sneakers, Leonard Edelman, was a consultant on Sneakers. So there actually are correct algorithm stuff. There is correct algorithm stuff in the movies. But although I think so, most people get the impression from media that algorithm means it's like spying on you software. I've never written any spying on you. So okay, back to carrots. So okay, what can you can do a lot with algorithms. I mean, algorithms are how you do something and get a result that you're going to be sure is correct, and how you do it efficiently. So that's sort of how everything you can do. I mean, everything you do with a computer is sort of going to involve algorithms somehow. So that's why I think that's why I think this course is important. But okay, back to Karatsubas, because I have, so I think Westbrook might have also written for Futurama, and he wasn't actually the only one. There's a graph theory paper, which I've cited. It was Westbrook and I forget the name. And they both went to be writers at The Simpsons. So, and there's also, there have been things like you can get YouTube videos about the math in The Simpsons. Anyway, okay, Karatsubas. Because otherwise it's going to look like I'm trying to bluff my way out of doing Karatsubas. Okay, so we split each of these in half. B is equal to the base of our number system, let's say is 10. So what is this? X, so x1, x0, y1, y0. So notice that this is x is x1 times 10,000, which is b to the 4. So this is n is 8. So n over 2 is 4. So it's x equals 5174 times 10 to the 4 plus 9672. That's just a dot, not a multiplication. Y equals 2385 times 10 to the 4 plus 4814. Now, what you would normally do is you'd say, okay, x times y is going to be x1 times b to the n over 2 plus x0. y1 times b to the n over 2. Why is that a capital? That's a small. That's a mess. The n over 2 plus y0. So you normally do 4 multiplications. X x1, y0, b to the n over, why do I keep making that a capital? N over 2 plus x0, y1, b to the n over 2 plus x0, y0, right? So you do this. So then, but we don't do that because that's four multiplications of n over 2 digit numbers. And that doesn't help us. Why is it b to the 4 and where? Here? Okay, because notice that why is it b to the 4 and not 8? Okay, so this 4 gets left shifted n over 2 spaces, right? So it's this 4 in the whole in x, this 4 is not a 4, this is a 40,000. So here we're going to have, so 5174 times 10 to the 4 is 5174,0000. So if you take this and this, each of these is a b to the n over 2. So when you multiply b to the n over 2, b to the n over 2, it's b to the n. This one and this one, there's only one b to the n over 2. This one and this one, there's only one b to the n over 2. And then x0 times y0, there's no b to the n over 2. Okay. How much time? 5 minutes. Okay. So what we're going to do, to do this trick, we're going to say, okay, z1 equals x1, y1. No, that's z2. Z1 equals x1, y0 plus x0, y1. And then z0 equals x0, y0. But, so this is still 4 multiplications. But Karatsuba's trick is to say, but this is equal to x1 plus x0 times y1 plus y0 minus z2 minus z0. Right? Because what's that? That's equal to x1, y1 plus x1, y0 plus x0, y1 plus x0, y0, and then minus x1, y1 minus x0, y0. So this disappears, and this disappears. So it's x1, y0 plus x0, y1. So now we're only going to do, we're going to do 2 additions, a multiplication, and 2 subtractions. So this is going to take only 3 multiplications. Now we do so this, maybe this is actually what the question was. So we're going to do the recursion where you can say, okay, why break with tradition? I might go overtime today as well for the last class. So T of n equals, well, what is the recurrence? The time for doing this multiplication, we're going to do, instead of 1 multiplication of 2 n-digit numbers, we're going to do 3 multiplications of n over 2-digit numbers. plus a bunch of additions and subtractions, which take linear time. So this is going to be like so like, okay, let's say, yeah, we worked this out in class. This is like 5, right? Some constant times n. I'm just going to say 5. Okay, in that case, what is A? A is equal to 3. B is equal to 2. F of n is equal to 5n. Okay, well, which case of the master theorem is this? Well, we have to look at log base 2 of 3 and compare it to f of n. And I forget which case this is. So the cases, remember, in the master theorem, the cases are, when you look at the recursion, the root is, most of the work is at the root, or most of the work is at the leaves. So the 3 cases in the easy version of the master theorem are either the weight is at the root, the weight is at the leaves, or the weight, you sort of like each level is equally weighted. So in this case, this is bigger than this. So it's going to be at the leaves, I guess. So anyway, it's going to be n to the log base 2. Right, so we plug it into the master theorem, which I don't have in front of me, but as you may have seen on the exams from previous years, if I ask questions about the master theorem, I actually paste the master theorem there. So we're going to get O of n to the log base 2, 3. And then this thing about, so this is getting rid of this b equals 10. That's just, yeah, okay, actually that's fine. We just leave it like that. Is that correct? That looks correct. Yeah, that's subquadratic. So that's like n to the 1.58 or n to the 1.85. I got that backwards on one of the assignments. See, that wasn't that bad. And I'm only 1 minute overtime. So the course is now over. Yay, I will never teach online again, I hope. Maybe I will a little bit, but I hope never. Okay, so thank you for being my class. Everybody who, no class on Wednesday, so that I'm going to get my coffee table back. And good luck on the exam. And with 4th year, no, I guess it might be office hours. There's no tutorials because the last day of class is Thursday. So we can't, the exam period actually starts on Friday. So we can't have a tutorial. That's why everything is due on Thursday, because that's the end of the teaching period. Thank you for being my class, all brave 9 people who actually stuck it out. But the office hours, I think, yeah, the TAs could run office. I mean, it'll be a bit tight having the office hours on Thursday when, oh yeah, usually the office hours are on Friday, Thursdays and Fridays, right? I guess we could have office hours on Thursday and have the assignment due on Thursday night for like the absolute last desperate hope. Yeah. Okay, so that was algorithms. Good luck with 4th year graduation, your careers in computer science. If you're around, so somebody actually did say hi to me in the park. I just had been running, and I was wandering on, thinking about something, and somebody said, "Hi, Travis." So now I'm going to, because I think I wrote on some assignment or something, say hi to me if you see me. So somebody did. So if that person sees this, hello. I was thinking about something else, so I didn't say hi back until they were also running, so they were passed by the time I said hi. But yeah, if next year, if you're still in Halifax and you see me on campus, I probably won't know who you are because I've never seen any of you. But say hi. Okay. Cheers. That's it. If there are any other questions, I can hang around for a few minutes, but everyone is free to go. And the little camera will stop recording in a second. So wait, how can we ask questions during the exam? Everything will be totally clear. I will be on, oh, that's a good question. This delicious Splendus lockdown browser. I don't know if I'm gonna bother with it because like, you could always just have another laptop beside it, in which case the Splendus lockdown browser is pointless. Or actually, I mean, I can't lock your phone, and I'm not going to. So somebody I was talking to said that they actually dropped the course because it required this creepy spyware. That the thing, and the person said that he couldn't find out where the recording was stored, and there were very not great guarantees about sort of privacy protection. I'm not going to do that. Yeah, so if I don't do the respondus thing, then you can just ask me. I mean, if it goes from like 7 in the morning, if I do this thing where I give you an extended time frame, so 7 in the morning until midnight, I'm not going to be awake that whole time. I could ask the TA. This year, the first year I posted my phone number. I think I'm not going to do that this year. That was maybe a bad idea. Yeah, you can ask me by email. I usually check email. So that's it. I mean, if you do the respondus lockdown browser, then you can't ask me by email, but you can by your phone. Okay. Yeah, we'll figure something out. I can always ask how people are doing. Oh, okay, the camera is done. So, oh, my coffee table. Can I get my coffee table? Oh, thank you. Oh, okay, somebody liked my course. Yeah, I like this stuff. I hope people enjoy it. Yeah, so good luck, and maybe see you around Halifax, the Hal, something. Okay. Now I'm hungry as well, so I can put it, and then I can eat something off my coffee table. So yeah, I will ask the TAs. So on Thursday, assignments 7 and 8 are due, right? I can ask the TAs to run an office. Is it due today? Okay. That's, yeah, because I did the correction. Oh, it's due today. Yeah, there are 3 questions on assignment 8. I can ask the TAs if they can run the office hour on Thursday. I'm not sure if I guess it's whatever assignment 7 says. It's due. Oh, actually, I probably didn't update it. It probably says it was due Friday, but in the email I would have said it's due. Okay. Good luck with assignment 7, 8, whatever. And cheers. Thank you again for being my course. this has not been like the most fun teaching experience ever. But thank you for getting through it with me. And it wasn't that the not fun part was not anything to do with students. It was to do with like, teaching in my den. Okay, cheers.